Welcome, my friends, to a place where we share inspiration and positivity. Thank you for choosing our video on metadynamics. Sit back, relax, and enjoy the ride. Metadynamics (MTD), also abbreviated as METAD or METAD, is a computer simulation method in computational physics, chemistry, and biology. It is used to estimate the free energy and other state functions of a system, where ergodicity is hindered by the form of the system's energy landscape. It was first suggested by Alessandro Laio and Michele Parrinello in 2002 and is usually applied within molecular dynamics simulations. MTD closely resembles a number of newer methods such as adaptively biased molecular dynamics, adaptive reaction coordinate forces, and local elevation umbrella sampling. More recently, both the original and well-tempered metadynamics were derived in the context of importance sampling and shown to be a special case of the adaptive Bising potential setting. MTD is related to the Wang sampling. As we progress through this video, let's shift our attention towards introduction and uncover its hidden depths. The technique builds on a large number of related methods, including in a chronological order the deflation, tunneling, turbo search, local elevation, conformational flooding, Engquist-Kullstrom, and adaptive Bising force methods. Metadynamics has been informally described as filling the free energy wells with computational sand. The algorithm assumes that the system can be described by a few collective variables CV. During the simulation, the location of the system in the space determined by the collective variables is calculated and a positive Gaussian potential is added to the real energy landscape of the system. In this way, the system is discouraged to come back to the previous point. During the evolution of the simulation, more and more Gaussians sum up, thus discouraging more and more the system to go back to its previous steps, until the system explores the full energy landscape. At this point, the modified free energy becomes a constant as a function of the collective variables, which is the reason for the collective variables to start fluctuating heavily. At this point, the energy landscape can be recovered as the opposite of the sum of all Gaussians. The time interval between the addition of two Gaussian functions, as well as the Gaussian height and Gaussian width, are tuned to optimize the ratio between accuracy and computational cost. By simply changing the size of the Gaussian, metadynamics can be fitted to yield very quickly a rough map of the energy landscape by using large Gaussians, or can be used for a finer-grained description by using smaller Gaussians. Usually, the well-tempered metadynamics is used to change the Gaussian size adaptively. Also, the Gaussian width can be adapted with the adaptive Gaussian metadynamics. Metadynamics has the advantage, upon methods like adaptive umbrella sampling, of not requiring an initial estimate of the energy landscape to explore. However, it is not trivial to choose proper collective variables for a complex simulation. Typically, it requires several trials to find a good set of collective variables, but there are several automatic procedures proposed: essential coordinates, sketch map, and non-linear data-driven collective variables. Brace yourself for an enlightening exploration of multi-replica approach as we dive into its profound implications. Independent metadynamics simulations replicas can be coupled together to improve usability and parallel performance. There are several such methods proposed: the multiple Walker MTD, the parallel tempering MTD, the bias exchange MTD, and the collective variable tempering MTD. The last three are similar to the parallel tempering method and use replica exchanges to improve sampling. Typically, the Metropolish-Hastings algorithm is used for replica exchanges, but the infinite swapping and Sawtooth algorithms give better replica exchange rates. As we progress through this video, let's now turn our gaze towards high-dimensional approach. Typical single-replica MTD simulations can include up to 3 CFs. Even using the multi-replica approach, it is hard to exceed 8 CFs in practice. This limitation comes from the bias potential, constructed by adding Gaussian functions kernels. It is a special case of the kernel density estimator KDE. The number of required kernels for a constant KDE accuracy increases exponentially with the number of dimensions. So MTD simulation length has to increase exponentially with the number of Ks to maintain the same accuracy of the bias potential. Also, the bias potential, for fast evaluation, is typically approximated with a regular grid. The required memory to store the grid increases exponentially with the number of dimensions Ks too. A high-dimensional generalization of metadynamics is It is based on two machine learning algorithms, the nearest neighbor density estimator NNDE and the artificial neural network ANN. NNDE replaces KDE to estimate the updates of bias potential from short-biased simulations, while ANN is used to approximate the resulting bias potential. ANN is a memory-efficient representation of high-dimensional functions, where derivatives Bising forces are effectively computed with the backpropagation algorithm. An alternative method, exploiting ANN for the adaptive bias potential, uses mean potential forces for their estimation. This method is also a high-dimensional generalization of the adaptive Bising force ABF method. Additionally, the training of ANN is improved using Bayesian regularization, and the error of approximation can be inferred by training an ensemble of ANNs. As we transition to the next segment, let's unravel the mysteries surrounding developments since 2015 and gain a fresh perspective. In 2015, White, Dommer, and Voth introduced experiment-directed metadynamics, a method that allows for shaping molecular dynamics simulations to match a desired free energy surface. This technique guides the simulation towards conformations that align with experimental data, enhancing our understanding of complex molecular systems and their behavior. In 2020, an evolution of metadynamics was proposed, the on-the-fly probability-enhanced sampling method OPES, which is now the method of choice of Michele Parrinello's research group. The OPES method has only a few robust parameters, converges faster than metadynamics, and has a straightforward rewriting scheme. OPES has been implemented in the PLUMED library since version 2.7. As we enter this new phase, let's uncover the impact of algorithm on our broader topic. Assume we have a classical n-particle system with positions at I in the Cartesian coordinates I. The particle interaction are described with a potential function v ver I. The potential function form e.g. two local minima separated by a high-energy barrier prevents an ergodic sampling with molecular dynamics or Monte Carlo methods. Now, let's shift our perspective and explore original metadynamics from a different angle. A general idea of MTD is to enhance the system sampling by discouraging revisiting of sampled states. It is achieved by augmenting the system Hamiltonian H with a bias potential V bias. HTV bias. The bias potential is a function of collective variables V bias. A collective variable is a function of the particle positions S senior I. The bias potential is continuously updated by adding bias at rate, where St is an instantaneous collective variable value at time t. A frac partial v at x b suffix sur partial t equal omega delta vic s vic st. At infinitely long simulation time t sim, the accumulated bias potential converges to free energy with opposite sign and irrelevant constant c. V bias at sim us st slim t sim v bias c. For a computationally efficient implementation, the update process is discretized into time intervals denotes the floor function and function is replaced with the localized positive kernel function Kelvin. The bias potential becomes a sum of the kernel functions centered at the instantaneous collective variable values sj at time. Via text via suffix saprox itor sumija level floor frac to text iter floor. Omega covic s ivic sj. Typically, the kernel is a multidimensional Gaussian function, whose covariance matrix has diagonal non-zero elements only. Via text via suffix saprox itor sumija level floor frac to text iter floor. Omega x per left. A fraca left frac vic s ivic s jervic iter right. The parameter, and are determined a priori and kept constant during the simulation. As we venture forward, let's take a closer look at implementation and its impact on our understanding. Below there is a pseudocode of MTD based on molecular dynamics and D, where R and V are their end particle system positions and velocities, respectively. The bias V bias is updated every n at nd steps, and its contribution to the system forces F is F bias. Set initial R and V, set V bias 0 every md step, compute CV values, st senior every n md steps, update bias potential, V at x biasavic S B at x biasavic S, a to mediates ber left, a fraca left fracvic S-civic S-tuvic sigma right compute atomic forces, avic Fi a frac partial vovic rho partial vic Ri over brace left, frac partial V at x biasavic Sir partial vic Sir right avic St. A frac partial vic spec rho partial vic I avic F at x biasi propagate R and V by it. As we embark on the next leg of our journey, let's unpack the layers of free energy estimator and examine its core elements. The finite size of the kernel makes the bias potential to fluctuate around a mean value. A converged free energy can be obtained by averaging the bias potential. The averaging is started from T-diff when the motion along the collective variable becomes diffusive. Barfavic S equal a frac at texts and T at x diff int out texts and T at x diff of x bisavic S, T, plus C. Brace yourself for a deep dive into applications as we explore its impact and relevance in our evolving narrative. Metadynamics has been used to study protein folding chemical reactions, molecular docking phase transitions, encapsulation of DNA onto hydrophobic and hydrophilic single-walled carbon nanotubes. In the next segment, we'll be exploring PLUMED and its implications for our subject matter. PLUMED is an open-source library implementing many MTD algorithms and collective variables. It has a flexible object-oriented design and can be interfaced with several MD programs: AMBER, GROMACS, LAMMPS, NAMD, Quantum ESPRES SO, DLPO LY4, SPC, and OPEN. With the groundwork laid, let's now examine other and its connections to our previous discussions. Other MTD implementations exist in the collective variables module for LAMMPS, NAMD, and GROMACS, ORIC, SPC, EDM, and Desmond. If you want to see more videos like this, make sure to subscribe and turn on notifications.